So now that we have a little bit of familiarity with chi-squared goodness of fit tests, let's do a couple more and then finish up the notes for this first section. So let's go back to our M&Ms example. Suppose we opened a bag of 60 M&Ms and counted the colors. The table shown the distribution of colors we found. So we have 9 blue, 8 orange, 12 green, 15 yellow, 10 red, and 6 brown, for a total of 60. And if we go to the M&M website, we're told the true proportions of colors distributed by the Mars Corporation is also shown below. So we want to know, with our null hypothesis, is the distribution of colors, or the distribution of colors will match that's claimed by the Mars company. With our alternative hypothesis, being the distribution of colors will not match the claim by Mars Corporation. So now we want to compare our observed count to the expected count. So what we need to do is actually come up with the expected count. So if I go over to my calculator, you see that I've done a little work before. I have our colors in with the counts, and then I also have our national percentage. So if I go to this equals line, and we know that we have a total of 60, then we're just going to multiply 60 times the national percentage. And if you hit enter, we get our expected counts. Again, these should all total up to 60. And then the next step, once we have our observed and our expected, is to calculate the residual. So the residual will be our color number minus the expected number. Additionally, if we wanted to look at our bar chart, we can select on our x-axis, we want to look at what the distribution looks like, so our color. And then if you hit menu and plot properties, we add a y summary statistic. And that one's going to be our color number. So we can see that there's a spike in yellow, but we want to see if that is abnormal in our comparison. So let's go back and we've calculated the residual. Now we want to calculate the residual squared. So I'm going to call that resid SQ, and that's going to just be RASD raised to the second power. Let the calculator in the spreadsheet do all the work for you. The last thing that we want to calculate after we square the residuals is the components that add up to our chi-squared statistic. So we're going to call that components. And that will be our residual squared divided by our expected value. So that's our expected number. And if we want, we then use the summation in our spreadsheet. So we type in sum, and we want G1 through, there are 6, so G6. And oftentimes, if you don't hit equals, like I didn't, it won't actually calculate the summation for you. So with the summation of all of our component pieces to our test statistic, we get a chi-squared test statistic of 10.1799. And as we know, we have 6 different colors, so that the degrees of freedom will be 6 minus 1, or 5. And what we want to do is, using our calculator, figure out what's the probability of getting this value. I'm going to hit menu, and we're going to go to statistics, our distribution, and then our chi-squared. So our lower bound is our test statistic, 10.1799. Our upper bound is a ridiculously large number, so on the notes it says 1 times 10 to the 99th. In this case, I'm just going to type in 99, with our degrees of freedom being 5. Additionally, because I can, I'm going to draw the shaded area, which is really nice when you've calculated all of these things. And we can see that in our 5 degrees of freedom, it's a little more skewed to the right. We have our shaded region, and our value, if I hit enter, is 0.07, or a probability of 7%. Now, testing at a significance level of 0.05, our p-value of 0.07 is bigger than 0.05. Thus, we fail to reject the null. There's not sufficient evidence to conclude the numbers published by Mars Inc. are incorrect. We just don't have enough information on that based off of this bag of M&Ms that we had. If you want, we can do this from our calculator as long as we have the lists. So I'm going to hit Control, Document, and I'm going to add a calculator. And what we do is we go Menu, 6 for Statistics, 7 for Tests, and then we're going to do a chi-squared goodness of fit test. So we want to look at our color number compared to our expected number. With, again, our degrees of freedom is 6 minus 1, or 5. And then we hit Enter. We again get the same test statistic, our 10.17, our p-value of 0.07, and a degrees of freedom of 5. And for those that want to see our component list or our contributions, if we hit vars, then we're going to go to stat comp, and this will give us the exact same column as our components that we calculated earlier. Let's try one more example. Suppose a market analyst wished to see whether consumers have any preference among 5 flavors of a new fruit soda. Sounds gross to me, but to each their own. A random sample of 100 people provided the following data. So we have our observed data for cherry, strawberry, orange, lime, and grape soda. Is there enough evidence to reject the claim that there is no preference in the selection of fruit soda using the data shown previously? And we'll set our significance level at 0.05. So if there is no preference, you would expect that each flavor would be selected with equal frequency. And as we can kind of see, this is already a chi-squared goodness of fit test. Got a random sampling, we got our counts, everything is over 5. So if everything was equal and we had 100 people randomly surveyed, our expected counts should be 20. So I'm going to enter 20 for each of these categories. Next, we're going to state our hypothesis. Our null hypothesis, the distribution of flavors is consistent with consumers indicating no preference. With our alternate hypothesis being the distribution of flavors is not consistent with consumers, meaning they're indicating some sort of preference. That's what we should make. Next, we find our expected values, which is equal for each flavor. So we have our 20 in each category. And now we're going to do the exact same thing that we did before. So we're going to find the residual, and then we're going to square it. We're going to compute the components. And we're going to find the sum for the sigma statistic. So we're going to say resid equals, you can just mouse over if you forgot what you've called the statistic. So flavor count minus exp count. So we'll do flavor count minus exp count. That's our residual. Our resid squared is going to be our resid raised to the second power. We are going to compute the components. So we're going to call that components again. And that's equal to the resid square divided by our expected count. And then what we want to do is sum all of these up. So we're going to type sum parentheses. Let's make sure we have equals. So we're going to type equals sum F1 colon F5 because we have 5 categories. And we get a chi-squared of 18 right on the dot. So again, if we want to run through our test, we are going to hit Control Doc on our calculator. We're going to add a calculator. And we're going to hit Menu, 6 for Statistics, 7 for Tests, and then 7 again for chi-squared goodness of fit. So we'll take our flavor count versus our expected count with our degrees of freedom of 4. And we hit OK. And we get our chi-squared test statistic of 18 as we saw before, and our p-value of 0.0012. This, testing at our alpha level of 0.05, gives us a p-value of 0.0012, which is definitely smaller than 5% or 0.05. Thus, we reject the null, and there is sufficient evidence to conclude the distribution of flavors is not uniform, and it shows a customer preference. And what we want to look at is if we go to vars and we go to stat comp and we hit enter, we can see which one of these flavors is actually having undue influence on our choices. And from our list, we had cherry first, and we see that cherry has 7.2, which is adding the most influence to our chi-squared statistic. So this concludes our first part of goodness of fit tests with the chi-squared statistic. And what we want to point out is, with our null hypothesis, the whole purpose of a goodness of fit test is to compare an observed distribution of counts to a theoretical or accepted distribution. In other words, we start with the null hypothesis and the expectations, rather than the alternate as we typically do with hypothesis testing. We are checking the fit against what is accepted as true. All we're able to do is reject or fail to reject the null that the theory, this hypothesized distribution, is true. We still never prove or confirm anything. We simply determine that the data are consistent with the theory, or the data is not consistent with a theorized distribution. The data comes from a single sample taken from a hypothesized population. So this brings us to the end of our first part with chi-squared tests. With part 3, we're going to talk about testing for homogeneity and independence.